Okay, good afternoon. It's a great pleasure to welcome you all to this special session in algebraic and complex geometry. And it's also my pleasure to introduce the first speaker for this afternoon. It's Sébastien Boucksom from CNRS and École Polytechnique. And he will talk about Kähler-Einstein metrics on Fano manifolds, variational and algebro-geometric aspects.
Thanks a lot. Well, it's of course a great honor and pleasure to be given the opportunity to speak on this occasion. So the purpose of this talk is to survey a number of recent developments in the direction of the Kähler-Einstein problem, whose goal is to understand when a complex manifold can admit a Kähler-Einstein metric. So as we will see, this problem can actually be approached by using the so-called direct methods of the calculus of variations. And this hopefully sheds some new light on the relation with the algebro-geometric notion of K-stability. Okay, so let's start by recalling a number of basic facts on Kähler metrics. So obviously here and at several other points in my talk there will be substantial overlap with the beautiful lecture by Donaldson this morning, but hopefully it's not really going to be a problem. Okay, so we'll be working over a compact complex manifold X. So it doesn't really need to be compact initially, but just before I forget to repeat this condition. And N is denotes the complex dimension of my manifold. So a Kähler metric is a special type of Hermitian metric on this complex manifold that locally derives from a potential. In other words, it means that the local matrix expression of the Hermitian metric with respect to local holomorphic coordinates can be expressed as the complex Hessian of some function, as indicated here. So the complex Hessian means these mixed second derivatives, holomorphic and anti-holomorphic ones. And somehow a miracle in complex geometry is that this condition is actually independent, well, it has to be, apparently, but it's really independent of the choice of coordinates. So one way to see that is to reformulate or re-express Hermitian metrics in the language of differential forms. We attach to a Hermitian metric its so-called fundamental form, which is a 1-1 form omega, whose expression is local, whose coefficients in local coordinates coincide with the ones of the metric attached to the matrix, attached to the Hermitian metric H. And this form is said to be positive because its matrix of coefficients is positive definite by definition. Now, in this language, the Hermitian metric H is Kähler precisely when omega is locally dd bar of some function, well, if you want, I dd bar of the function u in the previous notation, and some version of the Poincaré lemma tells us that this is actually equivalent to omega being closed. And we thus get one-to-one correspondence between Kähler metrics and Kähler forms, which are by definition positive, closed 1-1 forms. And in practice, we will mostly confuse the two objects, and yes, as is common in the subject. So Kähler metric admits, by the definition I adopted here, local potentials. But in this global compact situation, it's more convenient, of course, to have a globally defined version of the potential. And that's possible precisely thanks to the dd-bar lemma in Hodge theory. So a Kähler form being closed defines a cohomology class in the de Rham cohomology in H2 of X. And it follows from the dd-bar lemma that any other Kähler form in the same class is dd-bar cohomologous to the given form omega. And as a result, we can parameterize the space of Kähler metrics in this given cohomology class in terms of so-called Kähler potentials, which are globally defined smooth functions phi, satisfying the condition that omega plus idd bar phi is positive, and hence a Kähler form. So the space of such Kähler potentials will be denoted by script h, and you can just observe that the ambiguity between the Kähler form omega plus idd bar phi and its global potential phi is simply, well, phi is not unique, but it's almost unique. It's unique up to a constant. But sometimes it will be important to keep track of this additive constant. So we next turn to Kähler-Einstein metrics, which are by definition Kähler metrics that satisfy the Einstein equation. In other words, the Ricci curvature is constant. So the Ricci curvature, as recalled this morning, makes sense for any Riemannian metric. And in particular, if you're given a Hermitian metric, you can view it, you can forget about the complex structure and view it simply as a Riemannian metric, and it has its Ricci curvature. But in the Kähler situation, the Ricci curvature of a Kähler metric H, or equivalently the Kähler form omega, we confuse the two things, admits a very nice interpretation. Well, it can be viewed as a 1-1 form, a closed 1-1 form, just as we passed from a Hermitian metric H to its associated 1-1 form omega. And this closed 1-1 form is locally given by the expression written here. So it's minus IDD bar of the log of the determinant of the matrix, the local matrix attached to the metric H. Okay, so omega is Kähler-Einstein, as already mentioned. If its Ricci curvature is a constant multiple of omega. It's a constant curvature condition, but at the level of this Ricci tensor. And the next thing is that, thanks to the above description of the Ricci curvature, we can, in fact, show that its cohomology class, the cohomology class in H2 of x, given by this closed 1-1 form, Ricci of omega, is basically the first Chern class of x. So there is a factor 2 pi that sometimes people absorb in this, well, some notation to get rid of that, but it's not very essential, of course. And the first Chern class of x, or maybe 2 pi first Chern class of x, is also minus 2 pi, the first Chern class of kx, where kx is the canonical bundle of x. So it's the holomorphic line bundle whose local sections are holomorphic forms of top degree n. And as a consequence of the previous thing, the existence of a Kähler-Einstein metric imposes a cohomological constraint on the manifold X, or somehow constrains its geometry from the point of view of classification. If we pass, so if Ricci of omega is proportional to omega, then at the level of cohomology, we get that the first Chern class of kx is proportional to the cohomology class of omega, which is positive in the sense that it's represented by a positive form. And this forces the canonical bundle to have a sign. So we have 3 cases, which I mentioned mostly as a matter of terminology. So kx can be positive, which amounts to kx being ample in the algebro-geometric perspective. And then we say that x is canonically polarized. Or x is Calabi-Yau if the canonical bundle is trivial, in this, at the level of cohomology classes again, the first Chern class is trivial. Or the canonical bundle is negative, which means that the dual, the anti-canonical bundle, is positive, ample, and then we say that x is Fano. So regarding existence and uniqueness of Kähler-Einstein metric, the 3 previous cases behave rather differently. So fixing the notation again, we assume that x is compact, x omega, well, x is compact, and omega is a given Kähler form on it. And we assume this proportionality condition that we just saw because it's a necessary condition to get a Kähler-Einstein metric anyway. So we assume that the first Chern class of kx is proportional to the cohomology class of omega. Then we have, so in the case of negative or 0 curvature, which corresponds to kx being positive or zero or trivial numerically, we have the classical results of, starting already with the work of Calabi in the 50s, and then Aubin and Yao in the 70s. They show that the cohomology class of omega, or given Kähler class, contains a unique Kähler-Einstein form or metric in this situation. So we have existence and uniqueness, and I won't really say more about this case, which has been well understood for a long time. Now, in the Fano situation, the case where kx is negative, so the positive curvature situation, things are not that simple by no means. So we assume that x is Fano. The first thing I want to mention is that there are obstructions to the existence of Kähler-Einstein metrics, And the oldest known obstruction, I think, is due to Matsushima in the 50s. He showed that if omega is a Kähler-Einstein metric, the existence of a Kähler-Einstein metric forces the automorphism group of X to be reductive. So maybe we mean so odd zero, so the identity component of the group of automorphisms. So that's a complex Lie group. With the algebra is the algebra is the space of holomorphic vector fields. And the group is reductive, means that it's the complexification of a compact Lie group, which, in fact, in this situation, is explicitly given as the group of holomorphic isometries of omega. And the second thing is, has to do with uniqueness of Kähler-Einstein metrics. So then uniqueness, Kähler-Einstein metrics, in the Fano case, again, are as unique as it gets. So if you have two Kähler-Einstein metrics in the given cohomology class, you can pass from one to the other by the action of some element in the automorphism group, or even odd zero, so it means you can reach that by the flow of a holomorphic vector field. So that's good, but still existence is not automatic, and it's not always true, because of the obstruction number one. So the simplest example, probably, is the blow-up of the complex projective plane, P2, at one point. So that's a complex manifold of dimension 2, and it's a Fano surface, which does not admit Kähler-Einstein metrics because its group of automorphisms is upper triangular, so it cannot be reductive. That's a simple example. So if you blow up 2 points, it's still the same problem, and then if you blow more points, then in fact you will have a Kähler-Einstein metric. Okay, and then, well, we have the following results, and the purpose of what I want to explain afterwards is to give an alternative approach to the theorem here. So people have been trying to understand under which conditions that pertain to algebraic geometry a Fano manifold will admit a Kähler-Einstein metric. So besides this obstruction, the reductivity of the group of automorphisms, the Futaki invariants also come in the picture. There are certain invariants attached to holomorphic vector fields on X that have to vanish if X admits a Kähler-Einstein metric. And then Tian realized that we should also consider holomorphic vector fields on degenerations, on limits of X as well, in order to guarantee, well, in order to get rid of certain obstructions for Kähler-Einstein metrics. So it can be the case that you have no holomorphic vector fields, the group of automorphism is trivial, and still the Fano manifold does not admit a Kähler-Einstein metric. So in the end, people came up with this condition of K stability, or technically polystability in this situation, which I will come back to later on in the talk. And then we have the following result by various people, so Chen, Nelson, Soon, and Tian. Berman, that's for the converse direction, so Kähler-Einstein implies polystability. And then another proof by Datar Sekeleidi, relying on the continuity method, the more classical continuity method of Aubin, as opposed to conical metrics for the previous, the other people there. Okay. So the first thing you want to do if you want to study the existence of a Kähler-Einstein metric is to convert the equation, the Kähler-Einstein equation, into a PDE, which is a complex Monge-Ampère equation for the potential of the metric. So to fix notation, X is Fano. I'm normalizing the cohomology class in some way, which is not important. And V denotes the volume of the given Kähler form, which of course doesn't have to be Kähler-Einstein at this point. And it's also going to be the volume of any Kähler form in the class of omega. Now the Monge-Ampère operator, so recall that we have this space script H of Kähler potentials. There are smooth functions phi such that omega plus IDD bar phi is a Kähler form. And all Kähler forms in the class of omega are of this shape. Now the Monge-Ampère operator takes a Kähler potential phi and maps it to the volume form of the corresponding Kähler metric. So that's omega plus IDD bar phi to the n. That we normalize to mass 1 because it's convenient somehow for us, but it's very much not important. So that's this smooth probability measure Monge-Ampère of phi attached to phi. So the name Monge-Ampère operator comes from the following local description. If you pick a local potential for omega, you write omega as IDD bar u locally, where u is some function. Then omega plus IDD bar phi is IDD bar of u plus phi. And then the Monge-Ampère measure actually has a density with respect to Lebesgue measure, which is the determinant of the complex Hessian of u plus phi. And so the determinant of a Hessian is the Monge-Ampère operator. And because we take the complex Hessian, it's the complex Monge-Ampère operator. And then we have the following basic fact that omega phi, the metric omega phi determined by phi, is Kähler-Einstein if and only if phi satisfies the following Monge-Ampère equation. Monge-Ampère of phi is a multiple of e to the minus phi times mu, where mu is a volume form determined by omega. So it's not just omega to the n, it also involves the so-called Ricci potential, but it doesn't really matter for us. So there is a certain volume form that you can describe in terms of omega, such that this equation, the constant c normalizes the mass because we have to normalize the mass in some way. The left-hand side has mass 1, but if you shift phi by a constant, the mass on the right-hand side will move, will change. So you need to normalize the mass by this constant. And then this equation is equivalent to the omega phi being Kähler-Einstein. So what's nice about this equation is that you can write it as an Euler-Lagrange equation, as the equation for the critical points of a functional, and then that's the very beginning of the variational approach that we want to pursue. So the first point, we have two sides in the equation, the Monge-Ampère of phi on the one hand, and e to the minus phi basically on the right-hand side. So the left-hand side is Monge-Ampère of phi. The Monge-Ampère operator admits a primitive, an antiderivative. It's a certain functional, E, defined on the space of Kähler potentials, whose directional derivatives are obtained by integrating against the Monge-Ampère measure. So that's the meaning of being the... So the derivative of E is the Monge-Ampère operator. And this functional E has a certain number of algebraic properties which are important afterwards. But I'm only mentioning these two. So because the derivative of E is the Monge-Ampère of phi, it's a positive measure, and therefore E is monotone increasing. The derivative is positive, so it's an increasing functional. And if you can compute the second derivative, it's not very hard to show that it's negative, so E is concave. But here, concavity is understood in the sense that we view script H simply as an open convex subset in the linear space of smooth functions. But at this point, there is no reason to think of any other notion of convexity or concavity. Okay, and then we get the following fact, that we have this so-called Ding functional, D, which is the difference of L minus E, whose critical points are exactly the Kähler-Einstein matrix. So here, L of phi is similarly a functional defined on Kähler potential, whose derivative gives us this measure e to the minus phi times mu, which is the right-hand side in our Monge-Ampère equation. And somehow this constant c that we had before is taken care of because we have the log here. So it's not hard to see that the derivative of d at a function phi vanishes exactly when phi satisfies the Monge-Ampère equation. But that's one functional whose critical points are the Kähler-Einstein potentials of Kähler-Einstein metrics. It's not the only one, and there is another very important one, which is the Mabuchi K energy, which is more complicated and that I will ignore in this talk on purpose, but it plays a role at some point that I've hidden under the rug. Okay, and then we have this important result of Tian 20 years ago. We show that the Kähler-Einstein potentials are not only critical points of the Ding functional, but they actually minimize the Ding functional. So the critical points are minimizers. And the second thing is that if you assume the group of automorphism to be trivial, which means that you have uniqueness of Kähler-Einstein metrics, if any, then a Kähler-Einstein potential will actually exist if and only if D is proper. So here, this notion of proper, we will come back to it later, because it's not only proper in the topological sense. We are dealing with infinite dimensional spaces. So it's a certain notion, meaning that D grows to plus infinity at infinity in some sense. Okay, we want something like that, some kind of coercivity to set up this variational approach. So this result suggests that, well, first of all, you could try to find a Kähler-Einstein metric by following the steps of a variational approach. You take a minimizing sequence for D, and you try to show that it converges somehow, but that's not going to happen directly in H. And it also suggests a convexity of D. So you can note that the functional E is concave, I mentioned that before, and the functional L is also concave. That's much more elementary. It's just a reflection of concavity of the log, or the Hölder inequality, if you want. So D is just a difference of two concave functions, and then on the face of it, it doesn't have any convexity property at all. But the theorem by Tian suggests that D should be convex in some sense, and you can think that a convex function of one variable that has a unique minimizer, which is what happened in the second point of the theorem, has to grow at infinity, for example. So even the second point is also somehow suggesting convexity. Okay, so the variational approach that we will set up goes along the following lines. So we are going to extend the functional D to a certain metric space completion E1 of singular potentials, a certain metric space completion of the space of Kähler potentials, with the following features. The first one is that this space E1 comes with a distinguished class of geodesics that connect any 2 points. The functional D is convex along such geodesics, so here comes the convexity that we were looking for before. So it's with respect to this metric structure that is not obvious at all if you just look at the space H before. Then minimizers of the Ding functional in E1 are still going to be Kähler potentials. So that's also something that will require an argument somehow, because minimizers doesn't need to be critical points in any obvious way, because there might be a boundary for E1 in somehow. And even if they do, they would be weak solutions to the Monge-Ampère equation, and then they don't obviously have to be smooth. And finally, once you have this, you are interested in the growth at infinity of this functional, the properness that we mentioned before. And then the good news will be that you will be able to test this growth by looking at geodesic rays in the space E1 individually. So if it grows along any ray, then it grows uniformly in all directions, which is, of course, again, not a trivial thing, because the space is infinite dimensional. There is no obvious compactness around. But still, that's the situation. So we first introduce a notion of weak solution to the Monge-Ampère equation that we are considering. But the space E1 that I've just mentioned can first be described in terms of pluripotential theory. So you can define it as a sort of monotone completion of the space of Kähler potential H, and it goes back to the work of Gage and Zeriai. So you look at functions which are now possibly singular that you can obtain as decreasing limits of sequences in H. And you impose for this sequence that the energy is uniformly bounded. Remember that the functional E, this energy functional, is increasing. So if you have a decreasing sequence, E of Vj decreases, but it could go to minus infinity, and you don't want that to happen. So these functions will be omega plurisobharmonic, omega PSH, because that's so meaning that omega plus IDD bar phi is positive, but now in the sense of currents. So the function phi will be an integrable function, upper semi-continuous, and omega plus IDD bar phi is positive in the sense of currents. That's the definition of an omega PSH function, and it's true because it's true for the phi j's, and a decreasing limit of PSH functions remains PSH. So now we have our space E1. At this point, it doesn't have a metric a distance defining its topology. It rather has a weak topology that comes from the L1 topology. Omega PSH functions are L1 functions. So you have the weak distributional or L1 topology. They coincide on the space of PSH functions. So this space E1 has a natural weak topology. And you can extend the functional E to E1 just by exploiting the monotonicity again. You just define E of phi to be the limit of E of Vj in the previous notation. And then this will give you a monotone increasing extension of E to the space E1, which is also easily checked to be upper semi-continuous with respect to the weak topology. And then if you impose the two conditions, for a trivial reason, it's unique. So there is a natural extension of E to E1, which is maybe just semi-continuous, which is not going to be continuous for the weak topology. And indeed, you introduce the strong topology on E1 as the refinement, coarsest refinement of the weak topology, with respect to which E becomes continuous. So that can sound like a very strange thing to do. Why would you want to introduce this topology? So the reason for that is explained by the next result, which summarizes many results by many people, I guess, but so was stated in that way in joint work with Berman, Essidieu, Gage, and Zeriai. So this reference will come back, will show up later, and will be just called the BBEGZ. Okay, so the first point here is that functions in E1 are singular functions, but they are not too singular, so they satisfy an exponential integrability condition. E to the minus phi is in LP for every finite p. The second thing, which is the justification for this strong topology, is that the Monge-Ampère operator, which was only defined for smooth functions, scalar potentials, can be extended continuously to the whole space E1 with respect to this strong topology. So it's quite delicate to extend the Monge-Ampère operator to omega PSH functions. You have to impose conditions. The classical work of Bedford-Taylor tell you that you can do it if you are dealing with bounded functions, but yeah, if they are not bounded, you won't have any reasonable extension. So here somehow you have a quite nice space with a decent topology with respect to which the Monge-Ampère operator becomes actually continuous. And then, well, you can look at a weak solution, a solution in E1 to the complex Monge-Ampère equation we were considering before. You take a function in E1 that satisfies Monge-Ampère of phi is proportional to e to the minus phi times mu. Mu is the same volume form we had before. And then the Monge-Ampère arsenal, so building in particular on the fundamental work of Yao in the 70s and many other things, will ultimately tell you that any weak solution to this equation is in fact smooth. But that's a reflection of the ellipticity of the Monge-Ampère operator, but that's by no means something automatic like this, because it's a nonlinear operator and it takes quite a fair amount of work to get this. But once you know that a solution is smooth, then it's in fact just a Kähler-Einstein potential as before. So these weak solutions are no more general than the previous ones we had. They are classical solutions. Okay, now regarding geodesics that have been mentioned before and convexity, there is a natural notion of convex path in E1. So this terminology goes back to Bube and Chen, I think. So you have a notion of subgeodesic or convex path. It's a path of functions in E1 parameterized by an interval I, such that the function of two variables, t and x, is omega PSH on the product. If you view t, you complexify the variable t. So you should remember that if you have a plurisum harmonic function on Cn, which only depends on the real parts of the complex variable, it's actually a convex function. So that's the same spirit. And geodesics in E1 can now be described. One possible description is that they are maximal subgeodesics. You think of subgeodesics as a convex path, and the maximal ones are straight segments somehow. So these are the geodesics. And they are characterized by the fact that the energy of phi t along such a geodesic is in fact an affine function. So if you have a subgeodesic, E of phi t can be shown to be convex, and it's affine exactly when you have a maximal subgeodesic, which is geodesic. Okay, and then we have the following important results that goes back to the fundamental work of Chen in 2000, who was trying to understand the regularity of geodesics with respect to the Mabuchi metric, connecting two Kähler potentials. He proved that they are C11. And in the end, so you go to more and more singular functions, and then the limits of this Chen geodesics will coincide with the geodesics we are talking about here. And okay, so the first point here is that E1 with the strong topology that we defined before is complete geodesic space, is a complete metric space with respect to a certain canonically defined metric D1, which is an L1 version of the Mabuchi metric. So I will not try to describe this. It's not so hard to write a formula, but we have this Finsler type of, we have a metric here that defines the strong topology, and the space is complete. So it's the completion of the space of Kähler potentials for this distance D1, and it's a geodesic space, which means that you can connect 2 points, any 2 points by a geodesic segment, which follows from the second point here, that geodesics as defined above, which are somehow the limits of chain geodesics, are length minimizing, so there are geodesics in the metric space sense. And any 2 points can be joined by a unique geodesic segment. Okay, so the geometry of E1 is somehow modeled on an L1 norm. So it's not going to be true that all geodesics in the metric space sense are geodesics in this pluripotential theoretic sense. And in fact, there won't be a unique geodesic segment connecting 2 points in general, but among the metric geodesics, you have this special class of pluripotential geodesics, which we are considering here, for which you have uniqueness of the segment. Okay, and then the next point is the following result. So first of all, the extension, so the Ding functional extends to E1 because the energy, it has two parts in it. The L of phi, which was basically the integral of e to the minus phi, and that makes sense on E1 because e to the minus phi is an integrable function. And E of phi, which is defined on E1 almost by construction, as we saw before. So D has a continuous extension to E1, and this extension is geodesically convex. So it's convex along geodesics as defined above. So that follows from an important result of Bernson on positivity of direct images. It's a consequence of that. And the second point is that, as I've mentioned before, so that's this BBGZ result. Minimizers of the Ding functional in E1 are still Kähler-Einstein potentials. So that was true in H for trivial reasons, because a minimizer of the Ding functional in H is a critical point, and therefore a Kähler-Einstein metric. And I'm saying that it's still true in this larger space E1. So the main point is to show that the minimizer of the Ding functional in E1 is actually a weak solution to the Monge-Ampère equation. And then by the results I've mentioned before, it has to be a smooth Kähler-Einstein potential. So we have our functional D, which is convex on the space E1, and Kähler-Einstein metrics that will exist precisely when the functional admits a minimizer. So to understand that, we are looking at coercivity, or the growth properties of this Ding functional. So a minor technical point is that, the Ding functional is translation invariant. If you add a constant to a Kähler potential, the Ding functional will be unchanged. So it cannot possibly go to infinity at infinity if you don't get rid of these constants. So you pass to the quotient space. You have an induced metric D1 bar. And then you have the following result, which tells us that coercivity of the Ding functional, so linear growth with respect to the distance D1, is equivalent to the fact that D just goes to plus infinity at infinity. That's the properness in Tian's theorem that showed up before. And the third point is that this is also equivalent to having D growing along each individual geodesic ray. So each non-trivial ray, meaning each ray which is non-trivial in the quotient space, because otherwise D would be constant. So for each non-trivial geodesic ray, if you have growth of the Ding functional along each non-trivial geodesic ray, then in fact it will grow in all directions in a uniform way. So this result is not exactly what Darvas and Rubinstein proved, but they introduced a new technique to prove coercivity for the Ding functional, which we used with Berman and Johnson to prove that 3 implies 1. So you contradict coercivity. You get a sequence of functions in E1 that contradict the condition here, and then you look at segments that connect a base point, let's say 0, to this sequence of functions contradicting coercivity, and in the limit you show that these longer and longer segments converge to a geodesic ray along which D will be bounded above. And that contradicts point 3. So that relies on some compactness that is quite non-trivial, and so to prove this, we actually play with the K energy as well, and there is some strong compactness for bounded entropy potentials that is hidden here. And as a consequence, we recover the result that was mentioned before, the Tian's result, which was improved by Fongson, Sturm, Weinkow to coercivity, linear growth, and Darvas-Rubinstein, they gave this new proof, quite different, using basically this metric space E1. So if you have a Fano manifold and no automorphisms, so uniqueness of a possible Kähler-Einstein metric, then you have a Kähler-Einstein metric exactly when D is coercive. So again, to understand this, so if you have coercivity, you can show that then it's not hard by some weak compactness argument to show that the minimizing sequence will converge to a minimizer of D, which will be a Kähler-Einstein potential, and the converse, the converse follows from the previous theorem. Okay, so at this point, somehow we understand, we have this, we know that a Kähler-Einstein metric on a Fano manifold will exist exactly if we assume that the automorphism group is trivial, which will be the case in our theorem afterwards. If and only if the Ding functional grows along each individual ray. And now the game is to restrict the set of rays you have to test and to show that a certain smaller set that comes from algebraic geometry is enough. And that's the K stability condition. So test configurations and algebraic rays. So first of all, that's a definition. So test configuration for our given Fano manifold is a certain. So you take your Fano manifold X that you polarize by the anticanonical bundle minus K, and you take the product with P1 minus 0, the complex projective line minus 0, and the test configuration is a compactification of that where you add some fiber over 0. So equivalently, it's an equivariant one-parameter degeneration of X that you can embed, for example, in some ambient projective space. So it's some gadget that talks about degenerations of X, equivariant ones. Now, if you fix the choice of some smooth metric on the anticanonical bundle with curvature omega, which we can do because omega lies in the first-round class of minus K, then we have a one-to-one correspondence between the following 3 objects. So subgeodesics on the one hand, S1 rotation invariant functions, omega PSH functions on the product of X with a punctured disk, and then S1 invariant metrics with semi-positive curvature, but possibly singular metric on the product of X with the punctured disk. So the reason why that's interesting is that then you can study the singularities. So you are interested in the behavior of a subgeodesic ray when t goes to infinity. That will correspond to the behavior of the metric you are dealing with near the central fiber, near the point 0, which is missing in the punctured disk. Okay, then you say that the subgeodesic ray is algebraic, or has algebraic singularities at infinity, if the corresponding metric on x minus kx, product with the punctured disk, extends in some reasonable way, say as a bounded metric on some test configuration. And then you can, so that's a way to say that the singularities are analytic or algebraic. They correspond to holomorphic functions. They correspond to some ideal sheaf, and this ideal sheaf corresponds in turn to a test configuration. Then the test configuration encodes the singularities of the ray at infinity, and it's uniquely determined by the ray. And conversely, you have this result by Chen Tong and Fong Sturm and other people somehow. I mean, Berman, I guess. So they show that conversely, well, in the end, what you get is that any test configuration conversely determines a unique algebraic geodesic ray if you insist that the ray starts at a given base point, say 0. So then what you have is that among all possible geodesic rays in the space E1, you have this much smaller set of algebraic rays which is in one-to-one correspondence with test configurations. So that's what Donaldson mentioned this morning. You can think of test configurations as living on the ideal boundary, the space at infinity, the boundary at infinity of E1 in this case. And that they are the points that you can reach by these rays that have nice singularities. So then what you want to say is that in order to test the growth of the Ding functional, it will be enough to do it on these algebraic rays. And okay, then the reason why that's interesting is that you will then be able to understand the growth along geodesic rays purely in terms of algebraic geometry, and this will be the K-stability condition. So an accumulation of the work of many people tell you the following things. You take you give yourself an algebraic geodesic ray that corresponds to a certain test configuration. And then you are interested in the slopes at infinity of the various functionals we've seen before. So first of all, you have the E functional, which is actually an affine function on the ray. So E of T divided by T is in fact a constant. So the limit certainly exists. And this constant can be described by some algebraic version of E that depends on the test configuration. So I will come back to this in a second. So you have a similar result for L. Then you get the result for D as well, because it's the difference of L minus E. And then for the D1 metric, similarly, you understand the slope at infinity in terms of certain quantity. So here, this E-alg, that's easy to describe. It's basically the top self-intersection of the line bundle L on the test configuration up to a certain proportionality constant, which is not important here. L-alg is quite different. So the algebraic version of the L functional, that's defined in terms of log discrepancies. So I won't really enter in the details of that. But that has to do with the fact that in terms of log discrepancies, you can understand the integrability properties of e to the minus phi, where phi is an omega, is a purely subharmonic function. So d-alg is just a difference. And this kind of L1 norm of a test configuration it's a positive quantity that you attach to the test configuration. It's a norm-like invariant that measures the non-triviality of the test configuration. Non-triviality corresponding to non-triviality of the algebraic ray. And then we get the following, we can state the following, in fact, weak version of the Yau-Tandon-Hudson conjecture that we proved with Berman and Johnson. So we impose this condition that we have no holomorphic vector fields except 0. So the group of automorphisms is trivial for Fano manifold. And then we have the following equivalent conditions. The first thing is X admits a Kähler-Einstein metric, which will perforce be unique by the assumption of automorphism group. The second condition is that the slope at infinity of the Ding functional along any given geodesic ray compares favorably with respect to the slope at infinity of the D1, the D1 metric. So in fact, this equivalence between 1 and 2, we already saw it before. So we already explained before that we can test that having a Kähler-Einstein metric is equivalent to D being coercive, meaning it grows linearly with respect to the distance D1 bar. And that can be tested on each individual geodesic ray, which is exactly this condition too. So that we already know. And then the third point is to say that it's enough to do it for the algebraic rays. So this, you ask for the same thing, but only for algebraic rays. The fourth condition is what is called uniform Ding stability. So it's just a translation of 3 once you have the previous result, which told you that d-alg is the slope at infinity of D, and that the L1 norm is the slope at infinity of the distance. Then the equivalence between 3 and 4 is just direct from the previous theorem. And finally, the last condition is that X is so-called uniformly k-stable, as opposed to ding-stable. That's mostly a matter of what you want to take as the algebro-geometric condition that is supposed to guarantee the existence of a Kähler-Einstein metric. So you could take 5 by definition as meaning that condition 4 holds. It's anyway a condition that involves some algebro-geometric invariant attached to all test configurations in a uniform way. So in uniform k-stability, you would rather have condition 4 with the Donaldson-Futaki invariant instead of this d-alg. Okay, so maybe I should I just want to comment briefly on this result. So as I've already explained, basically, the main thing to show here is to prove that 3 implies 2. If you have a comparison of the slopes at infinity of the Ding functional and the metric along geodesic algebraic rays, then it will propagate to all rays. So of course it's an approximation result. You have to approximate a given ray by algebraic once in such a way that the slopes at infinity will converge or satisfy some semi-continuity in the right direction. So that's the main contribution that we did. That relies on multiplier ideals and important regularization results due to the Mailly. Okay, so my time is over, but maybe I can just show you this slide just for fun. Okay, so I'm just mentioning a number of further, more recent developments. So the first point is to say that people basically, well, Fujita, Odaka, and Bloom-Johnson have introduced a certain stability threshold that can be described in terms of the singularities of divisors defined by sections of multiple of the anti-canonical bundle. So it's an invariant that governs k-stability, and the point I'm mentioning this just to say that this looks a bit less, maybe a bit more accessible than the k-stability itself, for which you have to look at all test configurations. And so people often say, I mean, it's quite hard to check k-stability for a given Fano manifold, and this criterion is quite useful. And so using some improvements, extension of the previous theorem, we can relate it to the so-called Ricci lower bound. And okay, and then the final thing is just to say that there is hope, at least, that the methods we used to prove the previous theorem, which rely purely on pluripotential theory, would extend to singular Fano varieties, which have become quite important for moduli problems and so on in recent work. Okay, so that's my excellent Portuguese. Thanks a lot.
Okay, thank you very much, Sébastien. Are there any questions from the audience? There is one there.
How is the positivity of direct images related to the convexity of the Ding functional?
The positivity of what, sorry?
The direct images, you mentioned Bernson's work.
Yeah, it sounds a bit strange, but so the Ding functional, it's the difference between this term L of phi and E of phi. So along a geodesic in the space E1, E of phi is affine. So we just need to know that L of phi is convex, and then L of phi was minus log of integral of e to the minus phi, and that's actually the Bergman kernel associated to the trivial line bundle that you write as kx minus kx, or kx plus minus kx. And then you apply Bernson's results in this very special case. It sounds a bit silly, but and actually it tells you exactly this. Well, plurisubharmonic variation, which amounts to convexity because of rotation invariance.
Okay. Any other questions? Okay. Well, if it's not the case, let's thank Sébastien again.